So first of all, I'd like to thank the organizers for inviting me to speak here today. I think one of my first talks as a PhD was at a SIAM student chapter conference in Galway, so it's nice to be back to do another one. And today I'm going to talk to you a little bit about mathematical modeling of in vitro drug release from drug-excipient granules. So this is work done by myself and Professor Michael Vinicky, as Inda said, in working in MAXI and also SSPC, which is the Synthesis and Solid State Pharmaceutical Center, which is one of the big SFI research centers. Okay, just to tell you a little bit about myself before I start, I did my PhD in University of Limerick in MAXI from 2013 to 2016. MAXI does a lot of work in industrial mathematics projects, as you'll know, so my PhD was on two separate industrial projects, one of which was on modeling of coffee extraction with Philips Research in Eindhoven. And the second project was on industrial cleaning of contact lenses with Johnson & Johnson Vision Care in Limerick. So two very different projects physically, but mathematically, actually, the models are quite similar. So it's modeling flow and chemical transport in porous media. So those were two quite fun projects to work on. You can see here the coffee project in particular led to a lot of public science events. So here I'm pretending I know about coffee cupping rather than just the mathematics of how you get to a cup of coffee. So following that, then I went on to do a postdoc, again in MAXI, but this time based in the SSPC with a multidisciplinary group. And this was on formulation design of drug products in the pharmaceutical industry. That would be with the pharmaceutical industry moving towards continuous manufacturing processes. So again, there was a little bit on flow and compaction of powders, so physical models, but a lot more on design of experiments, data-driven models in support of experimentalists. So that was quite different. So it's good this year to be back doing a postdoc, which is more on what I did during my PhD, which is on modeling of drug dissolution. So again, back to modeling transport in porous media. And while these tablets look quite a bit different to coffee grains, actually the models that we use to model extraction are quite similar. Okay, so I'm going to do a couple of slides on introduction, just to give you a background on drug delivery, drug release, and specifically dissolution. So pharmaceutical drugs are administered using a variety of different delivery systems. You'd be familiar with a lot of these, so tablets and capsules, injections, and so on. And in particular, then tablets and capsules fall into the category of what's called oral solid dosage forms. And the absorption then of an oral solid dosage form into your system, first of all, you take it orally, as the name suggests, and then the absorption depends on release of the drug substance, so whatever the active ingredient is in the drug from the product. Following that, once the drug substance has been released, it has to dissolve in whatever conditions are pervading in your body. And then once it's in solution, it has to work its way across the gastrointestinal tract. So the idea of doing in vitro dissolution testing or dissolution testing in the lab is that if these first two factors are rate limiting in terms of the drug uptake, then the in vitro dissolution performance might be predictive of what actually happens in the body. If the third factor is rate limiting, then you're going to be less focused on in vitro dissolution. So we're going to assume that the first two factors are rate limiting. Okay, so a little bit of chemistry then. What is dissolution? Well, it's just defined as the process of a solid substance entering a solvent to yield a solution. In particular, if you're looking at drug release from an oral solid dosage form, it's not just dissolution, it can be a lot of other processes. So on the right-hand side here, we have a schematic of a typical dissolution apparatus. So this particular apparatus is called the paddle apparatus. So we have a stirrer, which is just a paddle. It rotates at a specified rotation rate, which might be roughly 60 RPM. And this is pure dissolution. So I have a solid drug particle, which is dissolving into solution. However, if you look at a tablet releasing, so this is my best effort at drawing a tablet. You might think it's more like a block of cheese, but I did my best. But in this case, it's not just dissolution is happening. You also have the solvent, first of all, getting into the tablet. Then if the tablet stays intact, the drug has to dissolve internally and diffuse out of the tablet. That's one possibility. Alternatively, the tablet might start breaking up, release the solid drug particles, and then you do get pure dissolution. So the problem then is all you get from dissolution testing is a drug release profile. And that profile gives you the percentage of drug released over time. So in this case here, it looks kind of linear. So that's called zero order kinetics. In this case here, it's fast at the start, it slows down. So this might be first order kinetics, and this then is some more complicated release profile. Okay, so then the challenge from experimentalist point of view is they need to know which process is dominating if they want to predict this profile here. Okay, so the message then from this slide, I guess, is just we're not just interested in dissolution, we're interested in the collective effect of all these different physical processes. And then finally, this is just one particular dissolution setup. You can kind of break down the different types of dissolution setups in terms of the apparatus. So the paddle apparatus is one. Another option is what's called a flow-through cell, where the tablet's placed in an enclosed volume and liquid is flowed through that volume. Or there's 6 or 7 other standardized setups you can use. You can also change the solvent medium. So if you want to simulate extraction in the stomach versus in the intestine, you might change the pH or the viscosity, which will also impact your release. And the last factor, agitation. You want to try and prevent any significant concentration gradients building up in the solvent, because that might limit extraction in a way that you might not understand. So unless you want to actually model the CFD of this system, you need to try and ensure that the system's well mixed. Okay, and before we get into modeling then, what do we want out of our models for dissolution? So there's the ideas here are based off a white paper from industry from last year, which kind of lays out the state of the art in dissolution modeling from the perspective of pharmaceutical formulation design, process development, but also what's called release testing. So before I talk about that, this is a useful schematic to give you an idea of the different processes involved in drug release from a tablet. So first of all, the tablet might be coated, and that coating might be designed to be rate controlling. So there's a rate at which this coat dissolves, then you get a solid tablet. Now that tablet might stay intact for the whole dissolution process, in which case you have drug leaching into dissolved form. Alternatively, for a fast releasing formulation, the tablet might disintegrate into granules, which consist of the active ingredient and some filler material. And again, those granules might be designed to stay together, or they might deaggregate. And then you do get your primary drug particles, and we're back to pure dissolution. And this step called K5 here is pretty well modeled in the literature, but the limitations are around modeling of these other processes. Okay, and then the idea is if we have good either physical or statistical models, we can start to understand what impact the physical and chemical parameters which the formulators are designing into these tablets are having on release, and that can lead to less experiments and faster drug development. Or another exciting opportunity in the pharmaceutical industry is the prospect of what's called real-time release. So if they can prove to the regulators that they understand how each of their process variables, which they can measure as the process is happening, so this is where continuous manufacturing comes in, they can then predict what the release is from each tablet. And if that process is robust enough, they can release those tablets as validated without having to do 5 or 6 weeks of lab testing and sampling to prove that. So this has already happened for a couple of different drugs. So it's certainly something that's coming down the line. And the limitations at the moment are some of these behaviors are complex, so the models need to improve. Okay, so this kind of summarizes some things I've talked about. There's several mechanisms that can be occurring concurrently, so it's important to try and understand what's rate limiting. The last mechanism, which was K5 in this diagram here, that's kind of reasonably well understood in the literature. So the focus for our work initially is on developing models for drug leaching from API, active pharmaceutical ingredient, excipient, which is the filler material, which could be just inert sugars or something like this. So to predict that process. So in this diagram here, we're sticking to K4, which is aggregate dissolution. Okay, and then down the line, if a number of these models are developed, and importantly, it's useful to develop and validate on sub-processes, because obviously that's a bit easier. Then we can provide a more complete model of drug release. Okay, so with that background now, we're going to just jump into the modeling. And we're going to start with a single granule. Later, we'll want to generalize that to model a distribution of different granule sizes. But first of all, we start with a single granule. It's porous, has a certain radius, and it's consisting of a soluble drug and an insoluble excipient. So the excipient is going to keep the structure of the granule. And that's introduced then to a well-mixed bulk solvent with a specified volume. So we're going to assume that the mixing process is working well enough to keep the solvent well mixed. Because it's insoluble, we're going to neglect break up the granule and assume that there's no significant swelling, which can be another complicating issue. And under that context, then there's 4 processes represented here, which have to happen for release. So first of all, the solvent has to infiltrate the porous medium. Then we need dissolution of the drug internally. Then the drug has to diffuse to the surface of the granule. And finally, then there's surface mass transfer for the drug to get into the bulk solvent. And the work here is going to consider the case where these first 2 processes happen fast, and the limiting cases are in-pore diffusion and surface mass transfer. And finally, we're going to assume spherical symmetry. So we've made a lot of assumptions, but the models we get are still mathematically rich enough to describe the situation that we're interested in. Okay, so now we're going to just define some of the variables we're interested in. So first of all, consider if we have a dry granule before it's introduced to the solvent, and it has different volumes, which we're going to represent as volume fractions. So the volume fraction of excipient is phi E, volume fraction of drug, phi D, and the rest is just air or space, if you like. So the initial porosity is phi 0. And to allow us to model some of the variations that happen in real granules, we're going to allow these quantities to depend on the radial direction in the granule, under the condition that, of course, the sum of the volume fractions has to be 1. So then that dry granule is introduced into the solvent. The solvent penetrates the granule as much of the drug dissolves as can, and that allows us to define this final granule porosity, which is just the sum of the volume fraction of drug and the initial porosity of the granule. So this is an important quantity. Also, we need to be interested in the saturation conditions of the drug. So there's a certain concentration at which the solvent is saturated and cannot take any more drug, which will depend on the pH and the temperature of the system. Okay, and then we represent our drug concentration, maybe in a slightly unusual form. So first of all, it depends on radius and time, so that's standard enough. But the concentration is represented per volume of the final pore space. So that's going to be important in setting up our different models. And with that in mind, then the initial drug concentration can be calculated from the volume fraction, the solid density of the drug, so the density of a solid drug particle, and the final porosity. So this is concentration per final pore space. Okay, and the reason for that will become kind of evident in this slide. So here we're looking at different possible models depending on the relationship between the initial concentration and the drug solubility. So we have specified a drug solubility, and now what we do is we compare our initial concentration to this drug saturation level. So first of all, if this level is less than the saturation level for all radial values, then all the drug can dissolve and we can assume it's all in solution within the granule initially. So essentially we have some specified initial concentration function, and this is going to extract in the radial direction under diffusion. Case 2 then is the most complicated case, and I'm not going to talk about it much today, but essentially this is the case where the concentration exceeds the saturation level, but only for some particular domains of the radius. So again, the schematic here I think is quite useful. This is the initial concentration, and it exceeds the amount of drug needed to saturate the solvent in these particular areas. So here, the solvent is saturated and there'll be no diffusive transport in these regions until the solid gets depleted, whereas there is diffusion in these other areas here. And then finally, case 3, which is the case we're going to spend most of our time looking at today, is where the initial drug loading is very high compared to what's needed to saturate the pore system. And in this case, we simply get the solvent comes in initially, as much drug dissolves as can, and the remaining drug is undissolved. And in this case, there's a zero diffusive gradient in the pore space, so essentially nothing is happening initially. Okay, so I'm going to jump straight into the equations in case 1. And this is where, as mentioned in the previous slide, the maximum value of the concentration function does not exceed solubility anywhere. So transport then is just governed by a mass balance and fixed law of diffusion. So this is the standard diffusion equation for a spherical geometry. The only difference is we have this volume correction term coming from the porosity. The boundary conditions are also pretty standard. There's a symmetry condition at the center. The surface condition comes from a balance between the flux of drug to the surface, which is this term here. And then on the surface, we assume that extraction to the external fluid is governed by essentially another diffusion process, which is proportional to the difference in the surface concentration and the concentration CB concentration in the bulk fluid. And we have mass transfer coefficient here. The initial condition, because all the drug can dissolve, comes exactly from this initial drug loading that we've concentrated or calculated. And then finally, we need to decide or set an equation for the bulk concentration. And to do that, we simply say we have a fixed granule size, we pick some number of granules, and the change in the concentration is just going to be controlled by N0 source terms from each of the granules. So we have this surface flux times the surface area times the number of granules. So this is a complete system, which we can go ahead and solve for case 1. So case 3 then is the case I'm most interested in for today. So this is again where this time the minimum of the initial concentration function, let's say it looks something like this, exceeds the saturation level at every point. So it's above the saturation level. So as I mentioned, if this happens, then the pore space becomes drug saturated and there's no diffusive transport. So essentially, if we didn't have this external bulk phase, nothing would happen then. The drug is stuck in the granule. However, we start to get a concentration gradient at the surface of the granule, which will deplete the concentration there until such point as it's below the saturation level. And in this case, what happens is we get a moving boundary. We denote it RD of T. And that boundary, as extraction proceeds, is going to separate a core saturated region from a shell region where extraction is happening by diffusion from this region through the shell region to the surface. So this is the problem set up in terms of concentrations. You can imagine it proceeding something like this. So the initial concentration, we have this moving boundary. The concentration gets depleted here until it's below saturation, and then our model starts essentially. So we get diffusion happening in this region, and for mass balance then this moving boundary moves until eventually it's going to reach the center. And when it does reach the center at some point, which we have to determine as part of the solution, the extraction then proceeds by diffusion. So essentially we go back to case 1. Okay, so again, the equations are here. I don't want you to worry too much about them because they're quite similar to case 1, except we have a couple of differences. As I mentioned, the drug loading in the saturated core stays as it is until such point as the moving boundary has reached that region. The equation for diffusion in spherical geometry is still here, but it's only active in the shell region. We have the same surface boundary condition at the interface between the saturated region and the region undergoing diffusion. The concentration is at saturation, so that makes sense. And then we have the same condition also controlling the concentration in the external fluid. So the only thing missing from this problem description then is what is happening to this moving boundary. So to derive that, we just invoke mass balance. So we need to have mass balance here. So we write an expression for the concentration of drug in the granule, and we just integrate, sorry, the total mass of drug in the granule. So we integrate the concentration over the radial direction. And if we differentiate that, being careful with that our limits here depend on time, we get an expression for the change in mass of drug within the granule. And for mass balance, then that just has to be balanced by the mass flux across the surface of the granule. So that gives us this condition here. And if we then apply the boundary condition 3 here, we can simplify this expression to give us an equation governing the motion of the moving boundary. And then we just need to add the initial condition that initially this boundary is at the surface. Okay, so now again, we have a well-defined problem for T is less than TC. So until the moving boundary reaches the center. Once it reaches the center, then, as I mentioned, we go back to case 1. So again, I'm not going to go through these equations in detail. We have the diffusion equation. Instead of a condition on the moving boundary, we have the symmetry condition again. And for our initial condition, we take the final solution from the problem for T is less than TC. And similarly here for the bulk concentration. Okay, so that's the model that we're going to look at. And for the analysis today, I'm going to restrict attention to case 3. But case 1 is also solved as a subproblem of case 3. So the only case we're not looking at is case 2. But if you want to ask me about that at the end, I can talk a little bit about that. Okay, so in order to understand our system, we non-dimensionalize using, I guess, the sensible scales. So we scale the radial coordinate with the radius, the moving boundary with the radius. We scale time with the diffusion time scale, first of all. Concentration is scaled with the maximum of this initial concentration function. And the bulk concentration, the scaling looks a little bit unusual here, but essentially it just comes from the volume of all the granules. So you can see the volume of a sphere here times the concentration of the granules divided by the volume of the bulk solvent. So that gives us a kind of scale for what this concentration is going to be. And if we substitute in those scales, we can reduce the whole system down to 3-dimensionless parameters. The first of which I call epsilon, which is giving you a clue. I'm going to consider this small at some point. So that's the ratio of the solubility to the maximum concentration of this initial concentration function. This is BI, so it's the mass transfer BO number. So it's quite common in mass transfer problems. So it's the ratio of surface transfer to internal transfer. And this parameter VR, again, it's called VR because I've called it a volume ratio. It's the ratio of the volume of all the granules to the volume of the solvent. Okay, and then in terms of interpretation of the parameters, epsilon, first of all, for case 3 has to be less than 1. And in particular, if epsilon is small, that indicates to us that the diffusion in the shell region occurs fast relative to the speed of the moving boundary. The BO number, I've said what it means, but in these problems, we expect the BO number to be large because internal mass transfer is usually limiting. And the volume ratio, loosely speaking, if we have a small volume ratio, then the volume of the granules is small compared to the bulk volume. So we expect to have sink conditions, or essentially the concentration of the bulk solvent isn't limiting extraction. Okay, so subbing in those scales and dimensionless parameters, we get our system of dimensionless equations. So again, don't worry about these. They're just the same as dimensional ones. We can see epsilon is appearing in a couple of places. At the moment, we're considering epsilon order 1, so that doesn't help us much. The only additional thing here is we can replace these two equations here, the ordinary differential equation for the bulk concentration, which is integral. And essentially all this is doing is invoking total conservation of mass in the system. So the concentration of the bulk can be specified by this integral term here. Okay, and then these equations are valid until the moving boundary reaches 0. And after that, we get the equivalent dimensionless equations that I specified previously. Okay, so if there's no further simplifications to be got, depending on the parameters in the problem, we just have to numerically solve this problem. So that's doable, but it's non-trivial. So essentially what you have to do is you have a moving boundary. So at least one approach is to immobilize that boundary using a change of variables. So we introduce xi here, which is just 1 minus the radius divided by 1 minus the moving boundary position. And that reduces our problem to being defined on 0 is less than xi is less than 1. So the equations become a little bit more complicated, but at least the domain is fixed. You also might have noticed that I didn't have an initial condition in the problem, and that's essentially, or at least in the shell region, and that's because the shell region is initially of 0 thickness. But if we want to solve it, we do need an initial condition. So we look at the limit of the problem as t goes to 0 and use the solution in that limit as the initial condition. And after that, I'm not going to say much about the solution other than we used an inbuilt solver in CompSol multiphysics, and we used the finite element method with quadratic elements on a uniform mesh. The only thing to point out, I guess, is, as I mentioned, this time where the moving boundary reaches the center has to be determined as part of the solution. So we just used an inbuilt events interface just to say at each time step, have we reached the center or not? And if we have, we need to change the equations for t is greater than tc. Okay, so now to go to the asymptotics. So one problem of interest, which does crop up in the solution testing, is where you have a low solubility drug, in which case the drug loading is going to be such that it's going to saturate the solvent in the pores. So again, in this case, we need to scale the concentration with this value epsilon. We need to change our time scale from being the diffusion time scale to being a long time scale, which corresponds to the time scale over which the moving boundary reaches the center. So the equations appear the same, except you can see now epsilon is cropping up in front of the time derivative. So at leading order, this term is going to be removed, and then we're going to have a quasi steady diffusion equation, which we can integrate. There's a slight change here where we redefine the volume ratio, where it actually becomes effectively a mass ratio. And essentially we need this to be small enough that our asymptotics would work. So there's some level of this value that's acceptable for this solution to work. Okay, so then we don't do anything too complicated. We just use regular expansion of our independent variables in powers of epsilon. We assume that this ratio is at most order 1, or in terms of our initial volume ratio, it's at most order epsilon. And that gives us these equations for our leading order approximations to our solution. So again, the usefulness is, as I mentioned, we can now integrate this, apply our two boundary conditions, substitute the answer in here, and we should get a single initial value problem for the moving boundary position. Okay, so if we do that, the concentration profile can be found as this ugly looking equation here. But as you'll recall, I haven't specified the porosity yet. So if the porosity is such that I can do this integral, this can be simplified significantly. So specializing to a constant porosity, the simplest case, this is the solution we get. So the concentration profile is depending on the moving boundary and the external bulk concentration. But as you can see, the integral isn't too difficult, so we could certainly do linear or quadratic porosity profiles without too much bother. Then we differentiate this, substitute it into the moving boundary equation, this one here, and we've reduced the whole problem to a single initial value problem for the moving boundary position with initial condition. And then provided the initial concentration function is simple enough, we can actually solve this. Okay, so we're moving towards a situation where at least we can write down an analytic solution, which we can at minimum use to compare to our numerical simulations to validate those, or hopefully it's also practically useful for some situations. So if we assume we really do have sink conditions, this volume ratio, we say it's going to be 0. We now have this initial value problem. And for certain functions of initial concentration, again, the easiest case would be a uniform concentration. We can find an analytic solution. So for uniform concentration, we integrate this, we get this implicit equation here. And finally, after all that effort, we do have a cubic equation for the moving boundary, and we can write down solution for cubic equations, even though they might not be so tidy. So we do have an analytic solution. I'm not going to try and put it on a single slide because it's quite messy. But what I will do is say that if we set the moving boundary position to 0, we can exactly find, in this case at least, the time for the moving boundary to reach the center of the granule. So at leading order, the estimate of this time only depends on, for constant porosity that is, the porosity and the BO number. And in particular, for situations we're most interested in, large BO number, this is going to tend to a sixth. And for order 1 BO number, or near the porosity essentially, it's going to be tending towards a half. Okay, so that's useful, first of all, for the prediction it gives us in the limit of low epsilon, and also for comparison to our numerical solutions. Okay, and just to mention then, even though I'm not going to talk about it further, we have generalized the model to describe a collection of granules. So typically you don't just have one granule size. You're going to have a distribution of granule sizes, maybe something like this. So this is volume fraction of granules corresponding to each radius. So the radii here are in millimeters. And we can generalize our model by picking a set of discrete radii for our granules, assigning a particular volume to each of our particular volume or mass to each of these radii. Most generally, if we want to model manufacturing biases maybe towards different porosities or concentrations in larger or smaller granules, we can specify these functions for each class. And then the solution just involves NP copies of our single particle model. And then we just need a generalized version of the bulk concentration equation to account for sources from each of these classes. So essentially, it's just a weighted sum of the single particle models. Okay, so finally then, to look at some results of the modeling. So first of all, we want to do a little bit of validation of our numerical solution and compare it to the leading order model. So we take some simplification, so a constant porosity of 0.2, so 20% of the volume, and drug concentration, which is constant. So the dimensionless concentration is 1. We have sink conditions, and we just take a range of different values of epsilon and the BO number. So initially, this table is just comparing the predictions of the time for the moving boundary to reach the center and the fraction of mass that has been extracted at that time. So if epsilon is really small, then we expect the numerical solution, which is here, to agree with the theoretical value calculated from the equation I just showed you. So if the BO number is 5 and the porosity is 0.2, then our equation tells us that the time to reach the center is 0.18, and the numerical solution gives us almost identical time, as we might expect. As epsilon increases, the agreement isn't quite as good, but as you can see, it's still pretty close. The fraction of drug released is over 99% in each case. So this tells us that when epsilon is small, the leading order model is really sufficient if all we're interested in is predicting the fraction of drug release. Because once that moving boundary reaches the center, even for epsilon is 0.1, there's less than 1% of the mass of drug remaining. And then the other thing I've just included as well is the time for the moving boundary to reach the center on the diffusive time scale. And all this is showing is the separation of the scales as epsilon gets small. So as epsilon is very, very small, diffusion really occurs much faster than the moving boundary. Okay, so then just a couple of plots to compare the profiles. This is the moving boundary position for a BO number of 5 and for 3 different values of epsilon that I've already mentioned. So the leading order solution is this black curve here. You can see the 2 smaller values of epsilon almost exactly agree, even if we zoom in at the end here. And for epsilon is 0.1, we can see the difference that we saw in the values in the table. And then also for the fractional release, the agreement is very good. Only in the case epsilon is 0.1 do we see that there's still some percentage of drug remaining when the moving boundary reaches the center. Okay, so then the profile of concentration within the granule is also interesting. So I've included here just the 2 larger values of epsilon, where the BO number is 5. So each of these curves represents a particular time relative to the time that the moving boundary reaches the center. So the moving boundary here is moving in, and you can see the concentration profiles in the solvent. So the black again is coming from the leading order model, and the blue then is the numerical solution. The leading order model only gives us solutions up to the point that the moving boundary reaches the center, because after that the concentration at leading order is 0. So this is the profile the moving boundary reaches the center. So you can imagine, given how steep this is, we have some numerical challenges here as well. And the only other thing that I want to point out is that for epsilon is 0.1, once the moving boundary has reached the center, we can really see there's essentially no drug left, whereas for epsilon is 0.1, there is some kind of significant drug concentration still trapped in the granule. Okay, so I think I'm coming up near time, so I have just a couple of more quick slides on experimental validation. So obviously it's all well and good to have a nice mathematical model, but we would like it to match with available experimental data. So this is an experimental study from 2013. It's a porous granule which has 30% drug and 70% excipient. So this is a schematic of the granule here, and this is partway into the extraction. So what they've done here is they have both the fractional release profile from the solution, but they've also imaged these granules during the solution using microcomputed tomography and some image analysis to try and identify the position of this moving boundary. And you can see here, there is this shell region where there looks to have been quite a lot of extraction, whereas we see less pore space in the center, so less extraction has occurred. So this profile is great because we can try and validate our model with not just concentration profile, which I'm sure we could fit anyway, but also a profile for this moving boundary. They have a range of granule sizes and porosities. We have all the parameters in the paper, except for the effective diffusion concentration, which we wouldn't expect to be there anyway, because it is an effective diffusion concentration. So what we did is we used this as a single fitting parameter to try and fit both profiles. So the results are here then. So these are this is the value of epsilon and 5 for the system, which is just one particular set of granules from the paper. The fractional release looks pretty good, I think. The moving boundary position, qualitatively at least, the behavior is similar. So I think given the assumption of the model, and I think difficulty in doing the experiment also, the agreement is pretty good. There's a lot more data, but I'm only going to show you one more comparison. So in this case, we have 3 different granule sizes. You can see the range of sizes here. So we would use the midpoint as the representative size. And here we've fitted the large granules. So we fitted this release. We've tried to predict the release for the smaller granules. So again, we do a reasonably good job, I think. And here, this isn't the radius, this is the percentage reduction in the moving boundary position. And for the available data, again, qualitatively, we have some kind of similar behavior. Okay, so just to conclude then, what have we done? Well, we've derived the model of drug release from a binary drug excipient granule. I guess the important part, we also have an allowance for variation in the pore volume or the drug loading. So during manufacture of granules, you can get a bias of drug towards either the center or the surface of granules, or also you can get the appearance of hollows in the center of granules. So this is something that the model could account for. Mathematically, it's a rich enough problem. We get a range of boundary value or moving boundary value problems to look at. And there's a nice asymptotic reduction as well. And finally, validation with the data is relatively promising. And we also have this generalized model for polydispersed collection of granules. In terms of future work, I think from the introduction, you'll have seen that the model we have at the moment obviously doesn't cover the range of tablet disintegration and dissolution mechanisms that are happening. So the first extension would be to look at solvent infiltration, swelling, and erosion. Hydrodynamics on the surface of the granules might also be interesting. I think in this case, because internal behavior is so rate limiting, it might not be so useful, but in other systems, the hydrodynamics are quite important. And then finally, at least a simple model of an eroding tablet, which could act as a source of granules, which could then be modeled using our equations, would be of big use to our industry partners. Okay, so thanks very much. And if there's any questions, I'd be happy to try and answer.